R3. So what we have to find is whether we can write any element, say order triplet xyz of R3, as a linear combination of these vectors, vector v1, vector v2 and vector v3. So let xyz, order triplet xyz, be an arbitrary element of R3, and we need to check whether it is possible to write xyz as a linear combination of v1, v2 and v3. And first we are assuming that we can write xyz as a linear combination of v1, v2, v3 as k1 v1 plus k2 v2 plus k3 v3. Now vector v1 is 1, 1, 2, vector v2 is 1, 0, 1 and vector v3 is 2, 1, 3. So that I can write this xyz as k1 times 1, 1, 2 plus k2 times 1, 0, 1 plus k3 times 2, 1, 3. k1 times 1, 1, 2 is k1, k1, 2, k1 and this will be k2, 0, k2 and this will be 2 k3 plus k3 plus 2 k3, k3, 3 k3. So adding them we will get, in the first position we will have k1 plus k2 plus 2 k3 and in the second position we will have k1 plus 0 k2 plus k3, that is k1 plus k3. In the third position we will have 2 k1 plus k2 plus 3 k3. So actually we are getting three linear equations here. Comparing the first coordinates, I will get k1 plus k2 plus 2 k3 equal to x. And from comparing the second coordinates, I will get k1 plus k3 equal to y. And from the third coordinate, we will get 2k1 plus k2 plus 3k3 equal to z. Okay. Now the problem is to find whether this system of linear equations is consistent. Consistent means the system has at least one solution. So whether this linear system has a solution k1, k2, k3 for every x, y, z. You give values for x, y, z, some real values for x, y, z. The system must have a solution k1, k2, k3. If this is true for any value of x, y, z, then we can say that the vectors v1, v2, v3 can span R3. If it is not possible, then v1, v2, v3 cannot span R3. If for some x, y, z, if the system does not have a solution, then v1, v2, v3 cannot span entire R3. Okay, so I can express this system of linear equations in the matrix form as this 1, 1, 2, 1, 0, 1, 2, 1, 3 times k1, k2, k3 equal to x, y, z. So if this system has a solution for any x, y, z, if and only if the coefficient matrix has a non-zero determinant. This is a theorem. Okay, so this system has a solution for any x, y, z if and only if the coefficient matrix has non-zero determinant. So let's find the determinant of matrix A. So to find the determinant of A, we will have 1 times 0 minus 1 minus 1 times 3 minus 2, then plus 2 times 1 minus 0, which is equal to minus 1 plus 2, which is 0. So here determinant of A is equal to 0. Therefore this system may not have a solution for some x, y, z. Okay, So the above system has no solution for every xyz. For some xyz, it will not have a solution. So we can say that the vectors v1, v2, v3 cannot span entire R3. So what we have is a system of linear equations. Suppose this x, y and z are 0, then we say that that system is a homogeneous system. If all the constants are 0, then we say that that system is a homogeneous system. So next theorem says that the solution set of a homogeneous linear system Ax equal to 0 of m equations in n unknowns is a subspace of Rn. So what we have is m linear equations and they have n unknowns, say x1, x2, etc. xn. And suppose Ax equal to 0 for some x not equal to 0, we have to show that this system, the solution set of this system is a subspace of Rn. So I am taking W as set of all x element of Rn where Ax equal to 0. That means we are considering every solution of the given system. One thing is sure, if I take x is equal to 0, 0, etc. 0 n times, this is an element of Rn, surely Ax will be 0. So at least 0 vector is here in the space W. So W is non-empty. Now what I have to show is this W is closed under vector addition as well as scalar multiplication. For that I am taking vector u and vector v from W. So vector u is in W means a vector u equal to 0. Vector v is in W means a vector v is equal to 0. Okay. Now what is vector matrix A times vector u plus vector v? It will be a vector u plus a vector v because matrix multiplication is distributive. So I can write a times vector u plus vector v as a vector u plus a vector v, which is 0 plus 0, which is equal to 0. So here I have matrix A times vector u plus vector v is 0. So vector u plus vector v is again a solution of the system Ax equal to 0. So I have vector u plus vector v is an element of W, or I can say that W is closed under addition. Now we have to show that W is closed under scalar multiplication. For that, A times k vector u is equal to k times a vector u, which is equal to k times 0 equal to 0. So I can say that this k vector u is again a solution of the system Ax equal to 0. So W is also closed under scalar multiplication. So if W is non-empty and it is closed under addition and scalar multiplication, we can say that it is a subspace of Rn. Since the solution set of a linear homogeneous system is a subspace of Rn, we will refer to it as solution space, not simply solution set. It is a subspace, therefore hereafter we will call it solution space of the system. We will see one more example, one more problem. Solve the following homogeneous system by any method and then give a geometric description of the solution set. And we have given a homogeneous system like this: 1 minus 2 3, 2 minus 4 6, 3 minus 6 9 times xyz equal to 0. So actually what we have is 3 homogeneous linear equations, means first row into column will give us x minus 2y plus 3z equal to 0. Second row times xyz will give 2x minus 4y plus 6z equal to 0, and the next one will be 3x minus 6y plus 9z is equal to 0. We have 3 equations in 3 unknowns. Now what I am going to do is I will multiply the second equation with 1 by 2 and third equation with 1 by 3, so that I will get x minus 2y plus 3z equal to 0. Again the second equation will be x minus 2y plus 3z equal to 0. Then again I have x minus 2y plus 3z equal to 0. All the equations are same now. So equivalently in the matrix form I will say that I will multiply the second row with 1 by 2 and I will multiply the third row with 1 by 3. So that I will get the new metric system in this form. Okay. Now what I am going to do is I will call this 1, this is 2 and this is 3. I will do 2 minus 1 and 3 minus 1. The second equation will be 0 equal to 0, third will be 0 equal to 0. Okay. Equivalently in terms of matrix I will say that I will change the second row to R2 minus R1 and third row to R3 minus R1. So R2 goes to R2 minus R1 and R3 goes to R3 minus R1, so that our system will be this. So actually we have only a single equation, x minus 2y plus 3z equal to 0. So any xyz satisfying this equation will be in the solution space of the given homogeneous system. Okay, so what I am going to do is I will give arbitrary values for 2 variables. Say I will say that y is equal to s and z is equal to t. Some value s and z will be given some value t. Equivalently I will get x is equal to 2s minus 3t. I can give arbitrary values for y and z, or any two for any 2 variables I can give arbitrary values. Then the value of the third variable will be determined automatically. For example, if I give y is equal to 0, z is equal to 0, I will get x is equal to 0. If I give y is equal to 1 and z is equal to 1, then I will get x is equal to minus 1. Okay, so 0, 0, 0 is in the solution set. Minus 1, 1, 1 will be in the solution set. If I give y is equal to 0 and z is equal to 1, y is equal to 0 and z equal to 1 will give x is equal to minus 3. So if I give arbitrary values for 2 variables, value of the third variable will be determined automatically. So x is equal to 2s minus 3t, y is equal to s, z equal to t for any real values s and t will be in the solution space of the given homogeneous system. Or we can say that any point x, y, z in R3 satisfying x minus 2y plus 3z equal to 0 will be in the solution space of this homogeneous system. Okay, now we have to interpret this solution space geometrically. We know what is meant by x minus 2y plus 3z equal to 0. It represents a plane passing through origin and having the normal vector 1, minus 2, 3. So the solution space of the given homogeneous system is the plane passing through origin and having normal vector n is equal to 1, minus 2, 3.